There are 15 organic and inorganic minerals that are currently under study in the human diet. The major classifications for minerals are based on the quantities that are needed daily. The major mineral class are those that are needed in amounts more than 100 milligrams per day, and the trace minerals are needed in quantities less than 100 milligrams per day. Just to kind of put that in perspective, if you added up the DRI or the RDAAI, and we'll distinguish that in a second, but if you added it up for all the minerals, it would come out to about 11, 12, 10 to 12, let's call it that, in total weight per day, which is equivalent to about 2/4 in weight. And of that, just potassium takes up about 5 grams or 4,700 milligrams, which is about the weight of a nickel. So again, we're talking about smaller constituents of our diet. You can see that the RDA and the AR adequate intake levels are provided. And for about a third, the actual RDA has been established. And for the other ones, just that adequate intake levels provided. And again, to distinguish between those, the adequate intake are just the ones where we look at people's daily intake of those, and they're generally healthy people. So we're going to go ahead and say that that's an adequate level. Looking at a little closer at the micronutrients that are in the food supply, and we aren't going to talk about all of them. In fact, I'll go back. I'll say we're just going to talk about some of the ones that are a little more problematic, the ones that we typically over and under consume for various reasons, whether it be that it's from, only really healthy vegetables, and even when we get our vegetables, it's not very bioavailable, or maybe we're of a certain region or ethnicity, or maybe we're of a certain gender. You can see the big gap between men and women in iron, and also between several other nutrients. So we'll talk more about the variability in these requirements as we move along, but we'll keep it specific to the ones that we typically over and under consume, and the ones that we really need to focus on in our daily diet. Minerals are measured in foods using techniques that are called ashing techniques. And there's dry ashing and wet ashing using chemicals. But dry ashing is the simplest technique, whereby you can put a sample in an oven at a super high temperature and incinerate all of the organic matter. So the high heat breaks down all of the organic carbon, hydrogen, oxygen, all that's released into gaseous forms. And all that you have left is that mineral or ash content. Now then they take those for sub-analyses, where they determine the specific amount of, say, calcium, iron, magnesium, and those amounts have been published in USDA food composition databases and other databases. I just like to use that same one for everything because I know it's going to always be available. The minerals that are listed in the USDA food database are these that are here, and sometimes you can search around on the web for less popular trace minerals like boron or arsenic or any other ones that you might be interested in, but these are the ones that are going to come in the USDA database, and even less are required on facts panels. So of minerals, the only ones that have to be there are the sodium, the calcium, iron, potassium. And I just highlighted a couple interesting notes here about the way that labeling works, just to we talked briefly about, here we're showing the ones that are required. And we talked earlier about, what the percent daily values mean in terms of our percent of that 2,000 calorie diet. But it's kind of nice to look deeper into the requirements and see that they are kind of providing a conservative safety window for making sure that we're providing good information for iron. So iron, it shows that 8 milligrams provides nearly half of the daily allowance. Now for a man, it would provide 100% of his daily allowance, which was only 8 milligrams. If you look back here at the amount of iron required, is 8 milligrams for men, and for women it's 18. So I thought it's kind of a nice little conservative measure to only call that half the daily values, and especially since there's no risk of iron toxicity at those levels, to double it up for men, but to represent that, hey, they might not be getting enough by only consuming, women might not be getting enough by only consuming 8 milligrams. Also looking a little closer, not so awesome is the sodium listing. This one shows that 160 milligrams is providing around 7% of daily values. And I calculated this backwards, and this would actually yield about 2,000 milligrams. And if we look back closer at the DRI, you can see that for sodium, we're looking in the zone of 1,500 milligrams. So in that one, there must be a little bit of a looser labeling law around sodium because it's a little higher than what's actually recommended. Now, again, that probably boils back to the fact that it's based on less good science. It's just an adequate intake value. And so using 7% of 2,000 isn't that big of a deal. This one's also conservative, calcium. And I like these conservative ones. It says that 260 milligrams provides 20% of a daily value. Well, as we'll learn in the nutrition for age section, elderly people need more calcium. And so this is being more conservative because that 20%, it's actually higher in the 1,000 milligrams per day required for healthy young people listed right here. But for older people, just to play it on the safe side, we want to list it pretty conservatively. So that's how minerals are presented on your foods labels that you're familiar with. We get minerals from animals. The most concentrated place that an animal stores minerals is in the liver, and it's sometimes in other glands, as we'll get into, like the spleen. But if you eat any of these organ meats, you're going to get a really concentrated source of minerals. Shellfish, obviously, being in the ocean environment where it's very ionic, they're obviously high in minerals also. And these are kind of, let's call them mineral superfoods. So if you just eat one serving of shellfish or organ meats, you're going to meet all of your daily intake needs for several of those important critical nutrients. The other place that we get minerals in animal sources is from dairy. And so milk does pass on minerals to newborns. And so, a newborn of any species is going to need those dietary minerals. And so we're going to also find those in fair concentrations in milk, not as high as those organs and shellfish meat, but in a serving of about 8 ounces or 1 cup, about a third of the DRI. So pretty good. We also get our minerals from plants, and plants provide a really concentrated source per 100 calories. But the problem here, and just being realistic with you in presenting how valuable plants are in terms of minerals, 100 calories is a lot of spinach and a lot of pure rice bran. And so this is the problem with quantifying spinach. If you could consume, 3 or 4, 5 cups of spinach to get 100 calories, then you would be consuming half of your daily intake for, what is that, 8 or so nutrients out of those 15 minerals that are required. So spinach is a really super mineral food. Same with rice bran, but same concept. You have to have a lot of it to get that half amount. But just in case you're looking for natural supplemental whole food sources, you can't do better or more mineral dense than spinach and rice bran, unless we went into more exotic food categories like algae and things and microbiological type fermented foods. But regular whole foods, spinach and rice bran is where it's at. However, the downfall of plant foods in terms of their mineral content are several factors, and we'll go into that in the point 3 section when we talk about absorption of minerals and bioavailability. But I want to show 2 here specifically, just because in the text I think I kind of highlight a little bit of the content, the oxalate and phytate content from some of these rich mineral plant sources. But oxalates are one compound that bind minerals and make them inaccessible to the human intestine for absorption. And phytate, you can see in this picture, this is an image of a phytate complex where it's done just that. It's bound to calcium or bound to magnesium or iron, important dietary minerals that bind or complex with phytate in these plant foods, and then they can't be absorbed by the intestine. And so plant bioavailability isn't awesome. And we'll talk more about that with details. Now, supplements have been developed, and again, talking the microgram amounts, we make supplements. People use supplements to meet their dietary needs for minerals all the time, especially for dietary calcium. But supplements are certainly a source of minerals, at least in the U.S. diet. And for these supplements, they're usually in the most bioavailable format. So we'll talk about some of those along the way, but usually like vitamins, they're really going to use ingredients that are most bioavailable, which is again why supplements are always used in fragile and scenarios and conservative scenarios like pregnancy and for gerontology populations. Let's see. Water is another significant source of minerals in the diet. We can't ignore water, especially if you consume tap water or municipally sourced water. It's typically a little higher in total solids or mineral content than bottled water, but certainly a significant source, and especially of those ultra trace minerals. And we're not going to talk a ton about those, but the leads and the boron and the arsen and the vanadium and several others that we're not even going to get into too much detail because we're not certain they're needed in the human diet, but they're certainly under study and are possibly important. So we do get lots of minerals, even those that aren't listed and that were not of crazy discussion in this upcoming lecture, but that do exist. We also get a significant source, and especially for a couple, a really good amount of our minerals from added sources. And these are used in foods as preservatives. So let me explain this a little bit without getting too food sciencey. Minerals in foods bind to water and take up what's called the free water in foods so that it's not available for the microbes. So microbes are naturally in food sometimes. It's a bummer, but that's why we have to keep it refrigerated, and that's why it can be potentially dangerous if it's not cooked all the way. So what we do to process foods, especially meats, and we're going to get into our favorite mineral that we overconsume next, but meats and other types of foods that spoil quickly, we put lots of sodium in them and I just said sodium, I blew it. We put lots of minerals in them and we bind all that water and we preserve them because it makes it unavailable for those microbes to use, and all that moisture being bound up prevents all types of chemical reactions that need and rely on free water, and those reactions contribute to spoiling. So all the way around about, we add minerals to foods for functional reasons and of course to make snack foods taste better. And so let's go ahead and get on with it. Sodium. Sodium's problematic. We overconsume it. It's overused in the food supply to preserve foods and to flavor foods and make them yummy. We also add salt ourselves at the table in quantities of anywhere from, a half a teaspoon to a tablespoon or more a day, depending on your preferences and your affinity for salt taste. Sodium is recommended at a level at about 1,500 milligrams per day. Now, it's a good time to distinguish salt from sodium. So salt is a compound that comes naturally in our foods, and it's obviously all over the earth, so it's very cheap, which is why it is the #1 mineral additive, again, to preserve foods. And it's obviously bound up with all kinds of other minerals too, like phosphate and nitrates and all kinds of other even organic things. But anyway, sodium is used a lot. But differentiating salt from sodium is that salt comes naturally in the planet, but salt is only 38% sodium. The other part of salt is bound to chloride. And so we quantify on the foods panels and anytime you see nutrition information, it should list only the sodium content, not the salt content, because sodium only represents 38% of salt. And so anyway, looking again back at the role of preservatives and the role of salt in taste and processed foods, you can see how meals are crazy extravagant, rich sources of sodium in the diet, and so are snack foods like pretzels and chips. Now I have listed up here really concentrated sources: turkey meat, pulled pork, orange chicken, my goodness, really, really strong, rich sources that are, 3-4 times the daily allowance, 2-3 times the daily allowance. But also we cannot forget our French fries and hamburgers and cheese pizza, which are also big time contributors to the daily salt intake in the United States. They're not as concentrated, but they're very, very high and consumed in high amounts. And again, we can't ignore same scenario with other snack foods that aren't as concentrated, but that are also consumed in high amounts. And also notice that even though pretzel sticks are slightly shy, actually that should have been should that have been bolded? Yeah, that should have been bolded orange too. Pretzel sticks are just shy of being a really high source of salt, but I mean, who eats 28 grams? That's 1 ounce. That's, probably, I wouldn't want to say, but maybe 12 pretzels. It's not a typical serving size. So anyways, I digress, but sodium, we overconsume it. It's in a lot of additives. It definitely comes from processed meals and snack foods. Zinc, I will try to keep it shorter. Zinc comes from primarily animal foods. It's going to be on the animal side of the spectrum. You can see seafood, poultry, beef, dairy. Those are going to be your concentrated animal sources. Notice something interesting. Even though poultry is not crazy high, I put it up here because dark meat is double of the light meat. And so something interesting, if you're low in zinc, always push dark meat. Formulated foods is where we get a lot of it. Designer juices like your Naked juices and Odwalla's, and a lot of those put zinc in there, like zinc oxides and different forms of zinc. Supplements come chelated, meaning, like we talked about earlier, sometimes in the intestine, minerals are bound to those plant compounds. And so if the mineral comes chelated already, it gets all the way unbothered and unbound all the way to the intestine with access to the enzymes that it needs to be broken down and absorbed. So it just gets it to its better local spot of absorption without being bound and interfered in the gut and then all the way down. So chelated zinc, and in fact, chelated other minerals are also a popular way to find mineral supplements. One interesting picture, in case you're wondering, I don't have it listed, but it is also a concentrated source in the diet, is dark chocolate. And I say dark because not milk chocolate, but like regular good old high percent cacao chocolate is a pretty good source of zinc too. So if you're a vegan or vegetarian, you can go for a vegan source of super high concentrated cacao chocolate, and that will provide a pretty good significant amount of daily zinc. Looking at calcium. Calcium is one of those things that it's pretty okay in plants, but plants have a lot of those compounds we talked about earlier that bind calcium. Calcium is like, if I could just call it fragile, it's like so susceptible. It's like a little baby. Everything that happens in the intestine, it just falls victim to, and it's just not very bioavailable. It binds to everything that comes in plants, and it just gets in the, and everything gets in its way. And so calcium is one of those ones that we get it from plants, but we also get a lot of it from synthetic sources that are more bioavailable, because in plants, again, it's going to come with that phytic acid, oxalic acid, and that fiber, which is going to really get in the way and inhibits its full maximum absorption potential. And we'll look at what those phytates look like a little closer in the next section. Looking a little bit closer, tofu, which is a product of soybeans, mature soybeans that are fermented and made into a product. Tofu is a good source, and we get most of our calcium in the United States from dairy. And you can see that milk provides about 1/3 of the daily intake, and plain yogurt will provide a little more than that because, again, it has less water, so it's more dense, more concentrated source of calcium. Looking at fortified, I love that they've targeted this breakfast area. So a lot of breakfast things have added OJ, and this has just kind of happened over time, but not only in the milk alternative category, like you see here with almond milk, most of those, like your coconut milks, any of those milk lines you see out now, soy milk, almond milk, coconut milk, they're all fortifying with calcium. And not that I'm sliding that into the breakfast category, but along with, calcium fortified orange juice, cereals, frozen waffles. So I think it's just kind of an interesting pitch, and it's smart to do that with the milk. Just makes sense to me too. But supplements, you'll see supplements come in all types of forms, but for vegans, you're going to want to look for algae and coral forms. Coral forms are pretty expensive, but again, they're going to be from those plant oceanic sources. A lot of calcium supplements come in a complex with D and magnesium, or amino acid complexed. And this goes back to the whole concept of like chelation, only they use amino acids with calcium. Too long of a story, but it makes calcium unavailable so that it can't get all messed up with those inhibitors of its absorption along the way, and it gets all the way to the right spot. And you're going to see those in, again, coral calcium is one good form, and again, sold with D3 or magnesium, or sometimes even chelated or bound to amino acids. Potassium. Potassium is one of those ones that it's required on the nutrition facts panel as of late, so it's a pretty important one on the diet, and I can see why. If you look at the sources, it's really coming mostly from fruits and vegetables. And seeds is a good source, but we don't, consume a whole lot of seeds as a whole, as a nation, I should say. So it's not a significant source of potassium. So we really need to get it from our fruit and our vegetables, but unfortunately we don't meet the recommended daily values for those, and so we're not getting enough potassium. Now, the consequence of not getting enough potassium is that we have balance issues with our pH. And so I'm not going to go into pH now. We'll get to that in the next section. But potassium in the diet is, should be discussed with, and it's not, but it should be discussed with, labeled with, and in association with bicarbonate, which is what it comes with in plant foods like bananas and potatoes. And we need them in that balance. And so the whole point of that is supplemental potassium isn't as effective. And potassium that we get from additives, because we do get plenty of it in additives. If I took you back here to sodium additives, it should be, if I didn't even list it, because that's how many sodium additives there are. Sodium, potassium included in there is one of them. But there's lots of sources of it. It comes as additives. And so point is we need it with bicarbonate, which only comes in plant foods. And we don't get a ton of those. And we need more potassium in the diet. And we'll discuss that more coming up. Iron in the diet comes from plants and animals, but big distinguish here is that plant iron sources are called non-heme iron. And just like the concept with vitamin A and vitamin D, where we talked about preformed sources, or even fats, where we talked about DHA and EPA, preformed sources. So the body, the human cell, or the mammalian cell makes these certain compounds that plants just don't make. And so animal sources of iron are called heme iron. They've already been synthesized into heme. They're preformed heme iron. And this is plain old plant iron, like in its real elemental iron reduced ferric form, ferrous form. So that's another little nice twist for you guys. That's ferrous. And that should also take us to the next concept of enriched iron. We get a lot of our iron from enriched products, and it's enriched with ferric acid, the same thing that heme is. So kind of again, to summarize on that, plant has non-heme iron, meaning that it's ferrous, it's raw elemental iron, and animal sources of iron have already synthesized that. It's preformed. It's already been made into heme, which is a type of protein, and that's called ferric acid. And when we fortify foods with supplemental iron so that we make sure we're getting enough, which we are, by the way, they use ferric acid, the more bioavailable heme form. So enriched products are really high sources, providing anywhere from 1 to 2 times the DRI. The little surprise, when peanut butter is a really good source of iron that people don't usually think about, and it's obviously supplemented. So if you're not big into fortified products, but I'm all about that for my kids, just because they're not big on taking little, Flintstone vitamins. So I try to integrate it in food stuff. But looking at grains, just to highlight the popularity with ancient grains, teff are really high in the grain category, and it's centered next to beans and leafy greens, which are even higher. But in the grain section, ancient grains are the highest. But again, it's not very bioavailable, which is a nice transition to the next section, which is mineral bioavailability, or digestion and absorption. Iron supplements usually come with vitamin C or ascorbic acid, so it can be reduced and better absorbed in the small intestine, which we'll get to in just a second. Iron is also one to bring up in terms of being kind of a worldwide problem, especially we're talking, about intake, so the food supply and where we get our foods and, the sources of iron in our diet as we know it. But iron is not a very available nutrient worldwide. And so a lot of folks, unfortunately, are iron deficient, and we'll get to what that means in a little while. But iron is a target for malnutrition and hunger because it has a very long setting deficiency, and then the symptoms manifest and they're very significant and serious, especially for pregnant people. In efforts, people feel differently about biotechnology, but I like to bring up the technology for students who are other types of majors, but bioengineered rice is certainly being developed so that it's higher in iron. And this has been experimentally going on with vitamin A and other nutrients that we may or may not have touched on in the past. But iron is definitely a target for worldwide genetic modification and figuring out a way to get people's iron status as a population better. Bioavailability, or mineral digestion and absorption, we start in the mouth, where with chewing and shearing, we're going to have mechanical changes that break down the foods. In the stomach, we're going to have all types of chemical changes and different, changes in the chemical form of the minerals. And the one I'm going to continue running on the example with is iron, because it's most confusing in how many times it changes as it goes through the absorption, metabolism, and storage process. So ferric iron is, again, from animals. And so animal iron, or heme iron, gets to the stomach, and it's reduced to ferrous iron, the kind that would have originally been consumed in plants by, ascorbic acid or something of the sort. Other minerals are also, liberated, especially those ones that are bound to proteins. Then later down in the small intestine is where minerals are actually being absorbed. Ferrous iron is being absorbed through heme transporters. Heme iron is being degraded to plain iron and bilirubin. And look, you can see here the transporters, and I wouldn't ask you to know those verbatim, but just to provide the level of detail if you needed it or wanted it, or we're going to advance onto some kind of pharmacological studies. It's nice to have this information. Looking at how calcium is absorbed, this one's a really fancy one. So calcium comes up to the epithelial lining. It hooks onto this TRPV membrane. Let's call it a protein membrane comes through, that activates calbindin down here. So calbindin is sitting down here, and it's activated, actually, by vitamin D coming by. So vitamin D comes along the basolateral down here, bottom of membrane of the cell, activates calbindin. Calbindin goes to start really sucking up calcium into the capillaries. So calcium absorption is kind of complicated, and you can see here, my main point I want you to see is this is why it's dependent on vitamin D, because calbindin is this mechanism that gets calcium in, and it's not activated unless vitamin D is present in the serum. And so, and I won't get into detail, that's actually not vitamin D, it's the activated form of D, which we talked about in the vitamin lecture. It's called calcitriol. ZIP is transported through the membrane through a ZIP transport protein, and then from there it's either absorbed or it's stored as metallothionein. And again, higher level knowledge, what I would want you to know from this is that there's a transition in the forms of iron. I would want you to be able to recognize that vitamin D is required for calcium, and I would hope that you would know that most mineral absorption takes place in the small intestine. If I didn't say that good enough. As we move on to the large intestine, electrolytes are dissociated and they're absorbed. So sodium, potassium, and chloride are pumped across using a sodium-potassium pump that channels those electrolytes into the blood and interstitial space from the large intestine into those spaces. Now we're going to proceed to the loss section, which comes out in fecal matter, and this is going to include small amounts of chromium, manganese, molybdenum, calcium, and magnesium, and those phytate complexes. So we mentioned earlier plant foods and certain, there's certain types of phytates and phytic acids in foods and higher amounts in other foods, but those in foods bind to minerals, you can see them there, and those minerals are excreted right out, unavailable for us to absorb. And we're also going to excrete out here bilirubin, which won't go into super complicated detail on, but that's from mineral metabolism. Let's look a little bit closer at mineral bioavailability. So we already introduced the concept of phytic acid and oxalic acid. And these are two, let's call them chemical compounds that are in plant foods. Phytic acid gets a lot of minerals, so it binds to several in the intestines and makes them unavailable for absorption. Oxalic acid is kind of calcium specific, so unfortunately a lot of the foods that calcium is high in, like strawberries and spinach, are also high in oxalic acid. Calcium is also itself an inhibitor of absorption of several dietary minerals, and this is why you shouldn't overconsume the amount of calcium in the diet. Polyphenols, which are also in plants, and fiber also affect fluoride, potassium, and magnesium absorption, which is another problem with potassium in that it is not only in plants and animals exclusively, for the most part, and in nice balance with bicarbonate, but it really gets inhibited in terms of its bioavailability by the other natural constituents in plants, like fiber and polyphenols. So potassium, I feel, is a tough one in the diet and may cause us some low-grade acidosis that just slippery slopes into other metabolic issues. Looking at things that enhance absorption of minerals, we have vitamin C or ascorbic acid. And what this does is reduce iron so that it is in a more absorbable form. And it also makes the absorption of chromium better. Protein also enhances absorption of magnesium and calcium, which is why they usually suggest taking calcium with a meal or some type of maybe even dairy product because it has protein in it to help with absorption. Looking a little closer, I don't have this one up here, but just showing you about mineral competing for the same transporters and the same absorption mechanisms, and why supplementation sometimes for bioavailability purposes isn't an awesome idea. So if you overconsume, say, zinc because you think it's going to help with your cold, or copper because you heard it helps with whatever, muscle strength or whatever, you can see that these guys compete for the same ZIP transporters. And when they get in, they're competing for the same enzymes to be stored, and they compete getting across the bottom or the basolateral membrane, same transporters there too. So if you have a ton of one of these, it's really going to occupy the balance between the absorption of these won't be right. So just to kind of point that out in looking at supplement absorption and bioavailability in the sense of mineral-mineral competitions. Electrolytes. So let's talk a little bit about after they're absorbed, where do they go? What is the distribution of some minerals? Well, some minerals stick around in the fluid. They're not actually going to do anything. They're just going to stick around in the fluid, and they're going to remain as part of the balance of electricity between the extracellular and intracellular compartments of the body. And the way that those electrolytes move in and out of the cell are through this ATP sodium potassium pump that I already kind of introduced down before, because it's also the same type of pump that they're absorbed into from the large intestine. So same type of pump moves them into the cells, into the extracellular and intracellular compartments, and to and from the different ones. Now, the extracellular compartment is divided into two spaces, the intravascular space and the interstitial space. Sometimes the intravascular space is called the plasma, or let's even call it the blood, but that wouldn't be perfectly accurate because the blood includes non-fluid compounds too. So the intravascular space, or the plasma, the fluid portion of the blood, or the interstitial space, which is the space between the cells that's packed with fluid, and the intracellular compartment. So this is inside the cell, or what we sometimes call the cytoplasm, the water-based solution inside the cell. The extracellular and intracellular compartments are made up of a balance of cations and anions that keep the fluid balanced between the two compartments. And so our body is a very sensitive balance of positive charges and negative charges that are completely dependent on this mineral balance. And so the main things to look for here are that sodium is the main cation in the body, being a very high of the total concentration inside those interstitial and intravascular spaces. And potassium is the one that's really high as a cation inside the cell. So now you know that potassium lives here and sodium lives here and here. And that's important because a lot of the ways that nutrients are absorbed, and a lot of even the changes that we undergo during pregnancy and undergo during aging, really do impact little teeny details like our balance of these electrons and our way that we balance water across these spaces. Looking a little bit closer at sodium homeostasis. So actually I should back up and say that these levels and concentrations of these electrolytes have to stay perfect, but specifically, and also notice here calcium, which you may not have known, that's an important cation in the intracellular compartment. And chloride is the largest anion component, or negatively charged ion, that exists outside in the extracellular compartment. And it's going to keep that balance between these two spaces just perfect. Of all of the mineral cations and anions in the intra and extracellular spaces, sodium kind of leads the show. So sodium levels are regulated, and sodium kind of leads what happens with other minerals in terms of their retention or their excretion or release from the body. So sodium homeostasis is regulated by the brain, and specifically the hypothalamus, which senses high or low levels of salt by osmotic pressure. So we talked a little bit about, how that water or fluid balance is maintained by those levels. Well, if that fluid balance starts to not be maintained, that means that too much salt or too little salt is present. So osmotic sensors in the hypothalamus sense, whoa, too much or too little salt, and they send a signal down to the kidneys, and specifically the adrenal cortex, which is a little gland that sits on the top of the kidneys. And we're not going to go through all the little series of biochemical reactions, but the result is that if the salt is too high, we go ahead and get rid of more in the urine, and if the salt levels are too low, then we keep it. And so it's this amazing mechanism in which we keep the exact amount we need by just secreting a little bit. If we ate too much, we let out more in our urine. And if we ate too little, then we let out less in our urine. And so we conserve it. We have this amazing balance called the Renin-angiotensin salt balance system that keeps our sodium levels dialed. Now, obviously, we have imbalances in our salt intake that affect our ability to do this perfectly because our kidneys only have so much of an ability to excrete salt. And we'll talk more about that coming up. Serum calcium levels, like sodium, are tightly maintained in the blood. And the way that serum calcium levels are maintained involve a series of reactions, glands, and organs. So it starts with the calcium sensing receptors in the thyroid gland, and they'll release parathyroid hormone, which activates the blood vitamin D to its active form calcitriol. And remember back when we talked about absorption of calcium, it takes calcitriol activating that receptor down in that basolateral membrane, activates that so that calcium can be absorbed into the bloodstream. So when serum calcium levels start to fall, the parathyroid hormone reacts by activating calcitriol so that we absorb more calcium from our foods. Another couple of action sites are also sensitive to calcitriol, including the kidneys and the bones. So at the kidney level, the kidneys are going to go ahead and resorb or retain more calcium instead of letting it go out in the urine. So that calcitriol is not only acting by absorbing more calcium at the intestine, it's also acting to make sure that the kidney retains more calcium when it's synthesizing our waste product. We also see the effects of calcitriol at the bone level. So calcitriol stimulates the bone to start breaking down and releasing that calcium and those free minerals into the bloodstream. And so we do this by breaking down our hydroxyapatite, which is that mineralized tissue in the bone. And so we provide, again, higher levels of serum calcium to maintain that tight balance. And so it looks kind of complicated. There's a lot going on, but really it's just a matter of low serum calcium levels signal that thyroid gland. Thyroid hormone activates vitamin D, and vitamin D has its effect in 3 spots to make sure that the body is retaining and absorbing as much calcium as is available. So iron is distributed and stored and also in the blood, maintained in a very tight balance in the body. So after we eat dietary iron, the majority of it is taken to the bone marrow, and it'll be used in a process called erythropoiesis, which is the stimulation of red blood cells. And we talked last time when we talked about some of the functions of vitamins. Vitamins are very involved in this process, not only stimulating erythropoiesis, but also they're those coenzymes and enzyme cofactors for a lot of the erythropoiesis processes. So a lot of the iron goes to the bone marrow. We use it to make red blood cells, and more importantly, the protein component heme, which delivers oxygen around. And we'll talk later about the functions of iron, but we're talking now about where it's taken and what happens to it, kind of like the fate. Some of the iron is taken to the muscle and similarly converted to myoglobin for transporting oxygen around inside the cell, and this occupies a small, about 5% of the total stored iron. Some iron is taken to the liver and it's stored, and really it's just a nice depot where we can store a large amount, and about 15% of body iron to be exact, and we can release that into the blood when serum levels are low. The spleen is actually responsible for iron homeostasis, so making sure that serum levels stay within that nice tight window. The spleen senses iron levels in the blood, and if needed, it will start breaking down its own stored iron, and it will also signal the liver to break down its stored iron to supply the bone marrow its iron that it needs to make red blood cells. So the spleen is an interesting thing in that it regulates iron levels and it also stores a pretty good amount of iron. And I think if you remember, we talked about good sources of iron include those organ meats, and this is why animals store a lot of iron in the spleen and liver tissue. Talking about the functions or the outcomes of minerals, we will kind of try to structure those similarly, looking at the structural and catalytic roles of minerals in the diet. So the most apparent functional mineral class are the bone minerals, and you can't get any more on the nose with structure than the bone minerals. These minerals provide the majority of what the bone and skeleton is made out of, and also the teeth. So obviously there's other constituents. It's not like they're all made of minerals. There's also protein matter, and there's blood, and there's moisture in our bones, but minerals make up a good 50 to 60% of the weight of the skeleton. And like I mentioned, teeth, and fluoride specifically has an interesting role in the teeth because hydroxyapatite, which we showed you earlier, is this calcified, calcium phosphorus complex. And fluoride is also used to remineralize tissue that's been broken down by acids. So fluoride is important for our teeth, which are exposed to acids and broken down. And then they're remineralized to make a compound called fluoreapatite, which is even stronger and more long lasting than the type our skeletal tissues have. So teeth have integrated fluoride, which again makes them very, very strong. Bone minerals not only play a structural role, but they also contribute to bone turnover. Magnesium, for example, and phosphorus is the initial laying down of hydroxyapatite, which is later calcified by calcium, but also magnesium literally stimulates the bone cells. So you're seeing here two bone cells. These are osteoblasts and osteoclasts, and osteoblasts are going around and making, and osteoclasts are breaking down bone cells. And magnesium and other factors, but magnesium specifically stimulates bone cell activity to maintain normal daily bone turnover. Bone minerals also play a role in maintaining calcium homeostasis. So like we talked about before, blood calcium levels are very tightly regulated, and this happens partially by giving up bone or resorption of bone from the skeletal tissues. So when serum levels are low, that calcitriol goes, hey bone, we need some, and the bone releases it. And so that's a big function, because we'll learn in a few minutes about the role of calcium, but it has a really important role in muscle contraction that we need adequate amounts of calcium always in the blood supply for. We also have structural roles for other minerals. So for instance, iron-bound protein. We talked before about how some of the iron goes to the bone marrow for erythropoiesis to make heme or red blood cells. Well, the name of that iron-bound protein is protoporphyrin, and I can't even say that word clearly, so I wouldn't expect you to know that verbatim, but that's the iron-bound protein that makes up our heme, and again, that delivers oxygen around. That's a very functional property of iron, and we'll learn what happens when we don't have iron in just a couple of minutes. Phosphate. So phosphate plays a lot of interesting roles. Number one, if you've been following with the whole muscle contraction thing, ATP, or how our muscle uses energy, our muscles' energies, our currency, I should say. Phosphate, adenosine triphosphate. So it's one of the compounds in ATP that we break off, and it releases energy for the muscle to contract. Well, phosphate has other roles too outside of energy metabolism. And if you remember, we learned in fats about lipids and lecithin, and we learned about different types of phospholipids. So phospho, as in phosphate, and you can see here looking at the structure of phosphatidylcholine, this is a very important structure of our cell membranes. So phosphate integrated into these phospholipids, like phosphatidylcholine, the one showing, these provide all of the permeability and selective permeability and flexibility, some of the great membrane characteristics that our cells have. So phosphate is an important component of these phospholipids, and thus a very important function. Electrolyte minerals. So another big way we talked about bone minerals. Another big way to classify minerals by function are the electrolyte minerals. And we talked mostly in this way about sodium, and I highlighted potassium and a little bit chloride. We looked at those three being like the biggest intracellular and extracellular cations and anions. And then we briefly a little bit looked at calcium too. So calcium is important both inside and outside the cell, and it's only there in a very, very small amount. So it's not that it's highly concentrated, but it plays an important role in triggering muscle contraction. So technically, outside of even water and pH balance, which I guess I'll go back to because I haven't hit pH balance, calcium and magnesium, but calcium specifically, but potassium, all of these cations and anions play a role in nerve impulse transmission. So it lets the cell know fire, and one of the big outcomes of that is muscle contraction. And so we could be thinking, skeletal muscle contraction like we're contracting our bicep, or more big picture like our heart. So that's why when we get to like mineral deficiencies and we talk about if we don't have them, we have irregular heartbeat, it's because, we have imbalances in those charges that we need to signal those nerve impulses from the brain. So that's one of the biggest functions of the electrolyte minerals. They're going to communicate and signal nerve impulses. One of the other functions of the electrolyte minerals, and we kind of glazed over this looking at electrolyte distribution, but water balance and pH balance. So we have to have those fluids perfectly balanced in those compartments, or we would have swelling, and we would have all kinds of osmolarity issues, and that creates pressure issues. And not to get too outside of things, but it creates pH balance and acidity issues. So we talked a little bit about potassium and bicarbonate, and sometimes they come together in plant sources. but potassium and bicarbonate are really important for balancing the pH of the fluids in the body. And so without potassium available, we tend to have a slight case of acidosis, which now I'm getting ahead of myself on potassium deficiency, but also one of the functions is to maintain that perfect neutral pH balance that we want for optimal health. We don't want to be outside of that range of nice pH. Catalytic minerals. So we spend a lot of time on vitamins talking about their catalytic role, and it's no different with minerals. Minerals play a role in lots of coenzyme functions. So we'll use our same little image of an enzyme, looking at the coenzyme, the enzyme cofactor, and the substrate. For instance, magnesium and molybdenum are both enzyme cofactors. Another, for instance, metalloenzymes include copper, zinc, and magnesium. And just copper alone, it's a coenzyme for these listed enzymes. And I got a little tongue-tied there, but there's lots of them. 6 super important enzymes. And I'll highlight the importance of a couple, but just from copper. So copper plays a role as a metalloenzyme, which does some whole recharging thing. Let's just call it recharges the enzyme. These metalloenzymes like copper recharge these enzymes and so that they're ready to be used again for another reaction. And just copper alone plays a critical structural and catalytic role in all of those enzymes listed. And just to give you an example, the lysooxidase is like critical for collagen function for your skin. Superoxide dismutase is the most important and powerful antioxidant in the cell. So some important compounds and enzymes that we're talking about. And also iron sulfur enzymes, which we already talked about iron, but another function is not only iron-bound proteins like heme, but other iron sulfur things like enzymes, which are also protein-bound, like we've talked about before. And also catalytic minerals, you have things like chromium that are playing roles as with hormones. And that's kind of what I used, I think, to symbol hormones last time. So I'm trying to keep consistent, but hormone plays a role in insulin and people's tolerance for insulin. So chromium is one of those that plays a role kind of indirectly in catalytic, because catalytic are kind of in that category of like regulation, making things happen, get it going. And hormones and enzymes for me are like in the same field in that way. So feedback, this is again looking at what kind of measures we make and what are the signs and symptoms and different things for imbalances, too much or too little in the diet. And we see lots of different clinical conditions that are outcomes of having imbalanced mineral intake. For instance, when we don't have enough of minerals, things happen like irregular heartbeat, and this can even be as extensive as death. But in the case that you have deficient potassium or hypokalemia, you could have a mild heartbeat issue, and you could also be in low-grade acidosis, which again over time is just a yucky metabolic condition to be in. It's more favorable to inflammation, it's more favorable to all kinds of infectious issues, and we're always just a little bit more overusing our systems when we're in a state of acidosis. So that could be an issue. Not consuming enough magnesium, you're going to end up getting kidney stones. You're going to have over-calcification of the soft tissues in there, and they're going to end up having to come out somehow. And from what I've heard, that it's no good. Calcium, low bone mineral density. So if you don't get enough calcium chronically, and also if you don't get enough vitamin D, like we talked about last time, I used the exact same image. You're not going to have very dense bones, because what happens is over time, calcitriol comes knocking at the door, and hence that's vitamin D, says, hello, we need some of that calcium for the blood, please, which is the priority for muscle contraction like the heart. And the blood goes, okay, here, and it starts breaking down its own matter and giving it up. It's really generous of it. But after a long time, low bone mineral density is an issue. So if you don't have enough iron in the diet, then you are likely to develop small and hypochromic or lightly colored red blood cells. And this is because you don't have enough heme being developed. So under a microscope, the blood cells don't look as rich and healthy. And in terms, they look smaller and paler in color. You also, if you spun them in a centrifuge or under centrifugal, I always have a hard time with that word, centrifugal forces, you would also see a lower hematocrit, which is the volume of packed red blood cells. So you can spin blood really fast, and however much packs down to the bottom, the height of that can be measured, and that's indicative of iron status. Sodium. So let's reverse the table and talk about what happens when we get too much. So sodium is one of those ones that we consistently overconsume. I wouldn't say that we consistently surpass the 22,000 milligram UL, but this causes a condition called hypernatremia, which is more commonly known as a clinical condition when there is too much pressure on the walls of the vessels, and this is called hypertension. And this is when the diastolic and systolic pressure are just too high. And over time, and we're going to get to this in the Nutrition for Disease and Health lecture, but over time, this causes, your vessels endothelial dysfunction. It causes your vessels to be impaired, and this causes inflammation and a big series of metabolic problems. So too much salt, while it seems pretty trivial that you just have too much in the blood and that, you can't quite excrete it fast enough and the kidneys can't keep up, it really is chronically a long-term big problem. Magnesium, if you get too much magnesium, and by the way, these are only like in experimentally induced doses. These are not natural, I ate too much spinach level doses. So these aren't regular occurrences for magnesium. But in the instances experimentally, it does cause dehydration and excessive thirst. But these are in cases 2, 3, 4 times the UL. Phosphorus and calcium are together in that if you get too much of them, you might see those same calcium stones in the kidneys and kidney stones that you had when you didn't get enough magnesium. And again, too much calcium and phosphorus just leads to too much laying down and calcification of soft tissues, which is kind of interesting that there can be mineralization in tissues where there are not osteoclasts and osteoblasts, and those are those bone cells. So kind of an interesting thing about the kidney that it can build up that calcium there just sitting around. It just goes to show that as amazing as the body is, it's just as susceptible to, anything as your cup sitting there collecting minerals at the bottom of it. Let's see. That's all I have on minerals. Thanks for listening.